Today we will continue with our optimization problems and we'll look at some surface area volume problems. So in this first example, we have a 200 centimeters squared of material available to make a box with a square base and an open top. Find the largest possible volume of the box and what dimensions maximize the volume. So again, lots of information provided. Okay, we have 200 centimeters squared. Okay, so that's going to represent the amount of material, which is surface area. And the box has a square base and an open top, so that's going to affect the surface area of the box. So first of all, let's just kind of put in some dotted lines here. Okay, so if the base is square, the length and width will be x, and there'll be some height h. So we're going to let x equal the length and the width. And h is going to represent the height. Okay, so right now we're given the surface area of the box is 200 centimeters squared. So if we think about the surface area of this box, it's going to be the area of the base plus the area of the walls. So the surface area is 200. The area of the base would be x times x, which is x squared. And the area of one wall would be x times h, and since they're all the same size, there's 4 of them, so there would be my surface area formula. Now we're asked to find the largest possible volume. Okay, so my second formula is going to be the volume of this box, which is x squared times h. And this is the formula that I'm going to have to take the derivative of because I'm asked to find the maximum volume. So I need to isolate a variable from my first equation, and h is the easiest one to isolate. So from my first equation, I am going to, first of all, subtract x squared over. So I have 4xh is going to equal 200 minus x squared. And then I'm going to divide both sides by 4x. And that would be my height. So now my volume is going to equal x squared times 200 minus x squared over 4x. So I just substituted the 200 minus x squared over 4x in for h. And now I'm going to simplify a little bit because this x will cancel out with one of those. And if I distribute, I'm going to get 200x minus x cubed. This is all over 4. And I can factor that as a 1/4 out front. So now I have my volume in terms of x, so now I'm going to take the derivative, so it's going to be 1/4 times the derivative is 200 minus 3x squared. And we want to figure out our critical numbers, so we want to figure out what makes the derivative equal to 0. So it's going to be when 200 minus 3x squared equals 0. So I'm going to solve for x, so I'm going to get 200 over 3 is equal to x squared. And then when you square root both sides, it's actually going to be plus or minus the square root of 200 over 3. And because x is representing a distance, we know that the only possible candidate would be the positive branch. Okay, and if I was to convert that to a decimal, now in our AP exam, we would not convert to the very end. We would go to 3 decimal places, but for right now, we'll just say this is approximately 8.165 centimeters is the length of x. So now I need to do a proof to prove that this is a maximum. So I'm going to use the second derivative test. And the second derivative is going to be 1/4 times negative 6x. Okay, so now if I take my critical value of 8.165 and plug it into the second derivative, this value is going to be negative, so therefore my graph is concave down, and therefore my critical number will be a maximum. So we know that x of 8.165 is going to give me the maximum. So the length and the width is 8.165. And to find the height, again, we can use the formula 20 minus x squared over 4x. Sorry, not 20, but 200. So 200 minus 8.165 squared all over 4 times 8.165. And if I work this out, this is going to end up being 200 minus 66.667 all over 4 times 8.165 is going to be 32.660. So this ends up being, I'll just do the calculation here, 4.082. So there would be your height. We know that the length and the width is right here. So now the last part of the question wanted me to find the volume. So to find the volume, again, it's going to be x squared times h. So it's going to be 8.165 squared times my height, which is 4.082. So 8.165 squared times 4.082. So this works out to be 272.136. And we do our final statement, and in our final statement we'll put our answer. So we would say the dimensions that maximize volume are 8.165 centimeters by 8.165 centimeters by 4.082 centimeters, and max volume is 272.136 centimeters cubed. All right, the only way they could change this question is they might give you the maximum volume and they might ask you for the minimum amount of material. So again, you would be taking the derivative of the surface area formula because you'll have a known quantity for your volume. But again, you just have to read the question clearly and see what they're providing you in the information in the question. Okay, taking a look at the next type of questions, we have poster problems. And in this one, we're told the top and bottom margins of a poster are 6 centimeters and the side margins are 4 centimeters. If the printed area on the poster is 384 centimeters squared, find the dimensions of the poster with the smallest area. So we have some printed material on this poster, and it tells us that the top and bottom have a margin of 6 centimeters. The side margin is 4 centimeters. And it tells us that the area of the printed part is 384 centimeters squared. So what we're going to do is we're going to let W equal the width of the print and L equal the length of the print. So this would be L, this would be W, and we know that length times width is equal to 384. Now we're asked to find the dimensions of the entire poster with the smallest area. Well, I need to come up with a formula for the area of the entire poster. Well, if I know that this length here is L, and I have a 6 on the top and a 6 on the bottom, the entire length is going to be L plus 12. And if I know this width is W and I have 4 on each side, I know the width of my entire poster is going to be W plus 8. So if I was to multiply these, I'd get W times L plus 8L plus 12W plus 96. Now we know WL is 384, so I can make a substitution. So I can say area is 384 plus 8L plus 12W plus 96. And if I was to collect like terms, I would get 480 plus 8L plus 12W. So now we'll go back to our first equation and we'll isolate one of the variables. So we'll say L is 384 over W. So in place of L here, I will put 384 over W. 480 plus 8 times 384 over W plus 12W. So area is going to be 480 plus 384 times 8 is going to be 3072. I'll bring W up to the top, so it's W to the minus 1 plus 12W. Now I'll take my derivative. The derivative of 480 is 0. The derivative of the second term is going to be negative 3072W to the minus 2, which is really W squared, plus 12. And now I'm going to figure out my critical numbers. So first of all, we can see that the derivative is undefined when W equals 0, but that wouldn't make sense in the problem because W is representing a width. So we need to figure out what makes the derivative 0. So I'm going to take this whole equation and set it equal to 0. So I'm going to add the 3072W squared to this side. If I multiply both sides by W squared, I'll get 12W squared is 3072. If I divide both sides by 12, I get W squared is 256. And if I was to square root that, I would get W is equal to plus or minus 16. And again, because it's a width, we can only deal with the positive case. So now we're going to do our proof to prove that that is a minimum because we want the smallest size poster. So I'm going to take the second derivative. And again, just to recall, my first derivative was negative 3072W to the minus 2 plus 12. So A double prime is going to be 3072 times 2. So that's going to be positive 6144W to the minus 3, which is really over W cubed. And if I evaluate this at 16, we can clearly see that I end up getting a positive value. So therefore my graph is concave up and my critical number is going to be a minimum. So now we have to go back and answer the question. And the question is, I believe we want to find the dimensions of the entire poster with the smallest area. So I found the width of the printed part. So now I can find the length of the printed part because it's 384 divided by W, which is 384 divided by 16, which is going to be 24. So that's the dimensions of the printed part. So this is 16 and 24, but we want the length of the entire poster. So therefore, the entire length now is going to be 24 plus 6 on top and 6 on the bottom is 12, which is going to be 36. And the entire width, 16 plus 4 on the left and 4 on the right, which is going to be 24. So therefore, we'll say our final statement with the units. So the dimensions of the entire poster with the least amount of material is 36 centimeters by 24 centimeters. Okay, let's take a look at one more. And this next example, we're looking at just a volume problem. And this one here is the only type that you're only going to need one equation to solve. So if we take a look at an example like this, we have a box to be made from a square piece of cardboard by cutting a square out of each corner, turning up the sides to form walls. Given the cardboard is 40 by 40, find the dimensions of the box that will maximize the volume. Okay, so we have a square piece of cardboard and we are cutting squares out of the corner. So you kind of get a visual of what's happening here. So when we're done cutting out the squares, we're going to get something that looks like this. And then we're going to fold up these sides along these seams and we're going to get a three-dimensional box. And our three-dimensional box will look something like this when we're done. Okay, so first things first, we know the entire original size of my cardboard was 40 by 40, and I'm going to let X equal the length of the cut. So let X equal the length of the cut. Okay, so that would be X. So to that, all of these little cuts are X. So now when you take a look at your final three-dimensional box, the length and the width are going to be the same. They started 40 units long, but I cut an X off both sides. So the length is going to be 40 minus 2X, and so 2 is the width. And if we fold up the box, this is the height right here, and that height is going to be X. So therefore, to find the volume, it's going to be X times 40 minus 2X all squared. Now I'm going to expand this, so this is going to be 1600 minus 160x plus 4x squared. So I'm going to expand this, so I'm going to get, the volume is equal to x times 1600 minus 160x plus 4x squared. And if I distribute, I'm going to get 4x cubed minus 160x squared plus 1600x. Now I'm able to take my derivative, so v prime is going to be 12x squared minus 320x plus 1600. So again, now I'm going to solve this, and I can solve it by trying to factor, or I could try to or I can use the quadratic formula. So if I use the quadratic formula, I'm going to get negative b, and b is negative 320, so it's going to be 320 plus or minus negative 320 squared minus 4 times 12 times 1600 all over 2 times 12. So this is going to be 320 plus or minus, so 320 squared, subtract 4 times 12 times 1600 is going to give me 25,600 over 24. So this ends up being 320 plus or minus the square root of 25,600 is 160. So I get two possible answers. X is going to be 320 plus 160 over 24, so 320 plus 160 over 24, or X is going to be 320 minus 160 over 4. So first of all, X is going to be 320 plus 160 divided by 24. This is going to be 20. And X is going to be 320 minus 160 divided by 24 is going to equal 6.67 or 667. Okay, those are your two possible answers for X. And X is representing the length of the cut. And if you go back to our original question, if the cut was 20 up both edges, you're going to have nothing left for your sides. So this first value of X being 20 is too big. So this is my only possible critical number. So now I'm going to do the proof. So I'll take the second derivative. So the second derivative was 24x minus 320. And if I evaluate the second derivative at 6.667, okay, so 24 times 6.667 minus 320, this is going to be less than 0. So therefore, we know my graph is concave down, and that critical number is going to be a maximum. So therefore, I can now answer the question, and the question was asking me to find the dimensions that will maximize the volume. So I know what the height is, and to figure out the length which equals the width is going to be 40 minus 2x. So 40 minus 2 times 6.667. So 40 minus 2 times 6.667. This works out to be 26.666. So therefore, my dimensions of the box are 26.666 centimeters by 26.666 centimeters by 6.667 centimeters. And that would be our final answer.